Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today we are at lecture number 20. This is week 10. Today's topics are open integrator and open differentiator. That is, open can be used to perform integration and differentiation functions. That is the mathematical function of integration and differentiation can be performed using operational amplifier. So today we will see circuits that uses op-amp to perform mathematical integration and differentiation. That is, for an input you will get an output that would be integral of the input. Similarly, for a given input, the op-amp differentiator will produce an output that would be derivative of that applied input. These topics you can see in section 10.5 of chapter 10 for your book Electronic Devices and Circuit Theory. So this is op-amp integrator. This operational amplifier, it is connected in this form with a capacitor introduced in the negative feedback, and an input is applied through a resistor to the inverting terminal, and the output of the op-amp will be the integral of the input applied. So whatever the input signal is, if input is a sine wave, then you will get integration of sine, which is cos, which is minus cos, and if you apply for example a constant at the input, which is DC, then the output will be a function of time t. That is, integration of a constant is t. Similarly, if you apply e to power x at the input, the integration of e to power x would also be e to power x. So this function will give you the mathematical integration. We will derive the output for this circuit if we have an input, and then see how the output would be as a function of input. So we will see the complete derivation of the circuit, how the circuit would work and produce an output that would be integral of the input. So mathematical integration can be performed using op-amp. The circuit that performs the integration function is shown in figure below, and a capacitor is introduced with the op-amp in the feedback. In order to derive the relationship of output to input, we can observe that the op-amp is connected in negative feedback for this capacitor. So as when the op-amp is in negative feedback, we can apply the concept of virtual ground at the inverting input of the op-amp. That is, if non-inverting terminal is connected to ground, actual ground, then the other terminal would be at virtual ground. So potential of this node would be 0. So with this fact, we can apply Kirchhoff current law at this node. With I1 and I2 defined at this node, I1 is entering into this node and I2 is leaving that node. With KCL, I1 would be equal to I2, where I1 is equal to V1 minus 0 over R. V1 minus 0 over R, and I2 would be equal to see dV by dt because I2 is flowing into the capacitance. As you can see, this I2 is flowing into the capacitance, and for a capacitor, if current is defined into the capacitor, charging this capacitor, then and voltage across the capacitor is VC and current is IC, then the relationship between current and voltage for a capacitor is given by this relationship, that IC is equal to C dV by dt, where VC is the voltage across capacitance. So we can write the equation for I2 as I2 would be C dV. dV is the voltage across the capacitor. That is, voltage across the capacitor would be voltage at this point minus the voltage at this point. This is the potential difference appearing across the capacitor. So voltage at this point is 0 and voltage at this terminal is V0. So 0 minus V0 is the voltage across capacitor. So dV by dt would be equal to C d of 0 minus V0 over dt. Now by simplifying this equation, we can write it as V1 over R. This is R actually, and not R1. V1 over R would be equal to C. This minus sign will bring out and will be written as minus C dV naught by dt, from which we can write this equation for dV naught by dt, that dV naught by dt would be equal to this will bring to the other side as minus 1 over RC into V1. And now at this point we can integrate this equation to find out the output. So integrating both sides of this equation as integral from minus infinity to t dV naught by dt into dt, that would be equal to integral at the right hand side as minus infinity, from minus infinity to t minus 1 over RC into V1 dt. So this derivative is cancelled with this, and integral is cancelled with the derivative. So we will get at the left hand side as V0. That would be equal to this is the constant into the integration. So here we can bring it out. So minus 1 over RC integral of minus infinity to t V1 of t dt plus constant of integration. So where then you can see that the output is integral of the input, where this constant of integration is coming from the initial condition, and if initial condition is 0, then this value would be 0, and your output would be equal to some constant minus 1 over RC into integral of V1 of t, which is the applied input signal. So this is how the output of an integrator is related with the input, and you can see that this circuit is performing the integration function. So where this 1 over minus 1 over RC is called the integrator time constant, and the value of C depends upon the initial condition. And now for an input DC of 1 volt with initial condition 0, what would be the output of the integrator that we are going to see. So as the initial condition is 0, so we can start our integration from 0 at before 0 before time t is equal to 0, the value of integrator value of the output is 0, and we are starting the integration after t is equal to 0. So from this equation we can see that V out would be equal to minus 1 over RC 0 to t V1 of t into dt. So this equation is is to compute the value of the output for an integrator with the initial conditions 0, and the circuit will start integration from t is equal to 0 up to any time t. This t is generic. You can perform integration to an arbitrary value of time. So let me see how the output of integrator would be for input of 1 volt DC or 1 volt step input, that is at t is equal to 0. The input goes from 0 to 1 volt and stay as at this value for indefinite time. So by plugging the value of input here to this resulting equation, we can find out the output as V out of t would be equal to minus 1 over R1 into C 0 to t 1 into dt, and integration of 1 is t from limit 0 to t, and by putting the limits we will get V out of t is equal to minus 1 over RC into t, where the output is a function of t. As t increases, the output magnitude would start decreasing because of the fact that it is multiplied by a negative. So at t is equal to 0, output would be equal to 0. At some instant greater than 0, the output would start increasing in the negative direction, and the rate at which the output would increase would be determined by this constant minus 1 over R1 into C, that is called the integrator time constant. So if this integrator time constant is the slope of this curve would be a function of 1 over R1 into C, where R1 or R into C. If this constant is increased, then this slope would increase. The response would be like this, and it would get constant. If this constant is reduced, the slope would be reduced, and it would follow this way. So for a step input, we will get a RAM output. That is, if you apply a step input, you will get a RAM output. The output would ramp up linearly until the op-amp goes into saturation. After that, the output becomes constant because of the saturation. So up till this point, the output will increase linearly, and the function of integration would you will get integration for a given input, and the integration is from output. The output of the integrator would until this point up to this point you will get the output that would be integral of the input. Similarly, for a sine as the input, you will get a sine output. So if the sine is applied at the input, you will get a cos function at the output or minus cos function at the output. This is actually minus cos. So the function will be like this, inverted. And because of the fact that it is an inverting amplifier, the output is minus of the integral of the input, and this minus and the minus cosine becomes plus cosine, so output will be this. So function input sine, output you will get a cos function at the output. And for a square wave input, you will get a triangular output. That is when input is positive, that is high, the output would have a negative ramp, and when input goes negative, the output will have a positive ramp at the output. So for a square wave at the input, you will get a triangular wave at the output of an integrator. There are some practical limitations for an integrator. The integrator we see in previous slides will produce the desired integration function only if the op-amp is ideal. But practical op-amp have some limitations due to which the simple integrator does not produce the desired output. So because of the problem that for a practical op-amp you have some limitations of DC offset parameters, and because of that because of that error voltage and current, the integrator that we have seen will not produce as such an integration at the output, and the output would not be the integral of the input if we use the circuit as is. So we have to do some modification in the circuit to use a practical op-amp to perform integration that we are going to see in the next few slides. So in order to understand this problem, let me do the analysis of simple integrator in frequency domain rather than time domain. So अभी तक जो हमने इंटीग्रेटर का जो एनालिसिस किया था वो टाइम डोमेन में इसको हमने एनालाइज किया था. हमने आउटपुट जो फॉर्म कंप्यूट की थी दैट वाज फंक्शन ऑफ टाइम फॉर आवर इनपुट एज अ फंक्शन ऑफ टाइम. सो दीज टू क्वांटिटीज output and input are function of time. This is the time axis for input and output. This is input, this is output, and they are function of time. So rather than in time domain, if we analyze the circuit in frequency domain, that is in frequency domain we replace the capacitor with the reactance. Or in Laplace domain, we represent the reactance as 1 over Cs. Then the circuit can be replaced in frequency domain as replacing the capacitance as capacitive reactance Xc. So this circuit would look like an inverting amplifier with feedback reactance, feedback resistance connected as reactance, and the input resistance as R. So the gain of this amplifier would be minus Xc over R. So output would be equal to gain times input, that is minus Xc over R into input. So by replacing the circuit in frequency domain with capacitance as a capacitive reactance, So the circuit would be an inverting amplifier that would give me output as an input by this relationship, and from this relationship I can conclude the gain as V out over V1 would be equal to gain, and it would be equal to minus Xc over R. So gain of the amplifier would be minus Xc over R, where X is the capacitive reactance, and which can be represented in frequency as 1 over omega c or 1 over 2 pi fc. So this will be minus 1 over 2 pi fc into R. So this will be the relationship for gain of the amplifier. So from the last equation which we have seen here, if we take the magnitude of this, then it will be equal to minus 1 over 2 pi RC. We said that we see that the gain of the integrator at 0 Hertz, that is when frequency is 0, the value of the gain becomes infinite. So gain will become infinite, and the op-amp will go into saturation, because if gain is very large, the op-amp is the output of the op-amp will be in saturation due to this high gain. So for the DC input or 0 Hertz signal, the input applied have 0 Hertz or DC, the op-amp will have gain of infinite, and the output would always be in saturation. That is, the value of Xc will be infinity and behave like an open circuit. So the value of Xc at 0 Hertz will become infinite, that it will be open circuit, and when there is no feedback in the op-amp, then the op-amp would be in open loop, and the gain of the amplifier becomes very large, and the output goes into saturation. So that means this integrator would not work for the inputs which are of DC nature, that is with very low frequencies, or frequency is 0 Hertz. So the value of Xc will become infinite, and the op-amp will be, and it will behave like an open circuit, so op-amp will not have any feedback at 0 Hertz. Now we can plot the response of the integrator, that the magnitude response of its magnitude as a function of frequency, as at low frequencies the gain is infinite, very large, and as the frequency is increasing, the gain will reduce with a constant rate, and the response will be the response will show a monotonic decrease in the gain of the integrator. So this is the response of an frequency response of an ideal integrator. Now even though you operate the op-amp at higher frequencies, so if you are not operating at DC, rather you operate it at higher frequencies, even then the simple integrator that we have seen would suffer from the fact that the input offset voltage which is a DC as well would bring the output in saturation. So the simple integrator have problem with any DC voltage applied at the input. The reactance of the capacitor will become infinity, and it behaves like an open circuit and the output goes into saturation. So to avoid this problem, we introduce a resistance in the feedback. As you can see that for this integrator, you add a resistance along with the capacitance in the feedback. So this is a modification in a simple integrator. The effect of introducing this feedback resistor is that it will now have a finite DC gain. Even when this capacitor becomes open circuit, the feedback will be applied through this RF resistance, and the closed loop gain of the amplifier is limited by these two resistors, RF and R. So with the feedback resistor RF, the DC gain would be minus RF over R. That is, if input is DC and at DC this capacitor is open circuited, and the feedback would be completed through this RF resistance, and the gain of the amplifier at DC would be equal to minus RF over R. So this gain would be the DC gain of the integrator. And for any DC offset voltage, the output would be limited by this gain, and the output will not go into saturation, as you are now having a finite gain. So for any DC input, with this finite gain, output would be a finite, and the operation amplifier would not go into saturation. So for any practical integrator, you will see a feedback resistor connected along with this capacitor to avoid the problem of DC shift. Now the frequency response of the modified integrator would also be changed, and the new response of the modified circuit would look like this, that it has now a finite gain at low frequencies, and as frequency is increased up to above a certain cutoff, the response will start decreasing at a constant rate. So as you can see, the integrator now show a low pass filter response whose cutoff frequency Fl is given by this relationship, which is 1/2 by RF into C, where RF and CF are these two components, RF and CF, that appears in this relationship for cutoff frequency Fl. So this is the cutoff frequency Fl at which the response start decreasing from its maximum value at DC value. Below this frequency, the integrator would simply work as an integrator. So from this frequency onward, the open circuit will start integration. And you can see that for an integrator, the response is having a linear decay, which shows an integration response, that is, output is integral of the input. So the frequency at which the gain becomes zero is called the unity gain frequency, as the response decreased. And now the frequency at which the gain becomes unity, this is called the unity gain frequency. This is the frequency at which the gain becomes 0 dB or equal to unity. This frequency is called the unity gain frequency. So unity gain frequency is defined here, where gain becomes 0 or 0 dBs. At 0 dB, the gain would be at unity, So it will be called unity gain frequency, and it can be found from the circuit by using this relationship that F0 is equal to 1 over 2 pi R into CF, where this R is connected as this resistance. So for the circuit to perform integration, that is this is FL, and this is FL. So this is the region between which this circuit performs can perform integration. So the signal frequency should be greater than FL and lower than F0. So in this range, for a signal frequency between FL and F0, the circuit would perform integration, and below FL the circuit would give a constant gain and behave like an inverting amplifier. So below the lower cutoff frequency FL, the integrator would simply work as an inverting amplifier, and if you keep the frequency in this range, the circuit will perform integration function. So this modified integrator has certain limitation on the frequency range between which this integrator will perform integration. Other than this frequency range, the circuit will not perform integration and will simply work as an inverting amplifier. The next topic is open differentiator. Next topic is open differentiator. This is the circuit of our differentiator, in which the output would be the derivative of the input applied to this circuit, that is V1 of t. As you can see that for our differentiator, the position of these two components is interchanged from the last circuit that we see in integrator. That is now the resistor is connected in feedback and the input is applied through a capacitor. So a mathematical differentiation can be performed using op-amp. The circuit that performs the differentiation is shown in previous slide. Differentiation function is just opposite of integration. Note that the position of resistor and capacitor is interchanged. Now in differentiator, for a step input, you will get an impulse at the output. As you have seen that for a step input for an integrator, you get a ramp at the output of an integrator. But if you apply a step input to a differentiator, you will get an impulse at the output. So for a step input, you will get an impulse at the output. So impulse is kind of this function. So for example, this is an impulse. This function you have studied in signal system course. That is the derivative of a step is an impulse. Similarly, for a ramp at the input, you will get a step at the output. This is the opposite function of integration. That is for an integrator, you apply a step at the input, you will get a ramp at the output. But for a differentiator, our ramp input will be step output. Similarly, for a cosine at the input, you will get a minus sign at the output. And for a triangular wave at the input, you will get a square wave. So this is a differentiator circuit in which you will get an output that would be the derivative of the input. Differentiator circuit shown in this figure 10.51, although it is not as useful as the circuit forms covered above, that is integrator is widely used and differentiator circuit is rarely used, but it has many applications in the control and other engineering disciplines. So the differentiator does provide a useful operation. The resulting relationship for the circuit is given by this equation, that is output would be equal to minus RC, this is the differentiator time constant, into derivative of the input V1 of t as a function of time. Where the scale factor minus RC is called the differentiator time constant. Now try to derive the above relationship yourself by following the similar steps we did for our integrator. That is, again, you can see that because of the negative feedback, this node would be virtual ground node, and you can define the current at each link and then apply KCL at this node and establish the relationship of these two currents using these input and output variables, and you can end up with this relationship. So try it by yourself at home. Also derive the relationship of these two cutoff frequencies, FL and F0, where FL is the cutoff frequency and F0 is the unity gain frequency of an integrator. Take it as an assignment. Let me call this as assignment 3 and derive the relationship, work out the circuit, and come up with the derivation of these two equations. That is the cutoff frequency of the low pass filter. This is a low pass filter that we have seen in chapter 9, that low pass filter has some transfer function, and from the transfer function you can find out the cutoff frequency, where the gain of the response is at minus 3 dB or 9.707 of the maximum value, and the unity gain frequency that where the gain becomes 1, and from that transfer function you can set the corresponding gain at these frequencies and try to derive the relationship. Take 3 to 4 days to come up with the summation of this assignment. I will post this assignment on Canvas, in which you have to derive the relationship and submit the working of your problem and to prove the relationship. So that's it for today from this lecture. We will have a question answer session in the coming week on Tuesday and Thursday. Allah Hafiz.